emission of a gluon. And this momentum was p, and we needed some convenient representation of this propagator. And I wrote that as approximately equal to u of p, u bar of p over p squared. So on shell, if p slash is on shell, that is p squared equals 0, then this is an identity, right? P slash is equal to the sum over spins of u of p, u bar of p, right? Now, in this problem, this momentum was not exactly on shell. However, it was very close to mass shell. And I was ignoring a lot of effects that had to do with the deviation of that propagator from mass shell. So all I can say is that up to order k, the order in which I was working, this is actually an accurate approximation. To just take this momentum, remember that momentum was E00 and E minus something of order k perp squared. Right. So to order k, which is the order in which I have to evaluate it, it's okay to ignore that term. And then this quantity can be represented in this way. Okay. Good. Well, let's get started. I've told you about the strong interactions, so now it's time to start telling you about the weak interactions. The weak interactions are, of course, of a very different character. The strong interactions are strong. They create bound states. They correspond to these objects called quarks that are not actually seen in nature. There are all kinds of odd problems associated with them. The weak interactions have odd problems of a different kind. They're mediated by vector bosons, just like the strong interactions, but they're mediated by massive vector bosons, the W and Z bosons. The mass of the W and Z bosons means that those interactions are short range, and for that reason, that reason alone would make the weak interactions weak, that is, amenable to treatment in perturbation theory. It's interesting to ask what the intrinsic strength of the weak interaction is. If I imagine an interaction that's mediated by a heavy boson, this propagator is g squared over mw squared, or maybe I should write g squared minus q squared over q squared minus mw squared. But if mw is very large, this is approximately g squared over mw squared. So now the question is, what's the mass and what's the strength of the coupling constant? So I'm going to argue in next week's lectures that coupling constant is of the order of E, the electromagnetic coupling constant, and that allows us to say what the mass is in a way that I'll explain at that time. For the moment, though, I'd like to tell you a little about the effective low-energy theory of weak interactions, which was deduced from the properties of elementary particles and their radioactive decays. And we'll leave the question of what this W boson really is until next week. Now, the weak interaction was basically the first thing that was known about kind of particle physics beyond just electromagnetism. You all know that the whole study of modern physics begins with an experiment where Becquerel put some material, some rocks, in a box with photographic film, and opened the box later and found that the photographic film had been developed. And this stuff turned out to be uranium salts. And so he realized that uranium was emitting some kind of high-energy radiation spontaneously. We all know today that that's the process of beta decay, which is the process neutron goes to proton plus an electron, plus it turns out an extra particle, which is neutral, called the neutrino. And actually, you all know by now that because the neutron and the proton are bound states, this must actually be a reaction of quarks. So in fact, the real reaction that would take place at this level would be a down quark turning into an up quark plus an electron in the neutrino. Similarly, if you look at muons, for example, that come from cosmic rays or from other sources, the muon has a very similar decay. The muon goes to a muon neutrino, an electron, and an anti-electron neutrino. And we're going to study this reaction in some detail in this lecture as a model of the weak interactions. Well, in the 1930s, Fermi wrote down an effective interaction for this process. And that interaction was used so then, with an effective interaction, you can take the matrix elements of that and models of the nucleus and try and organize the systematics of beta decay. But things were really not very well understood. And this continued to be true until the 1950s, when people got a crucial clue about the theory of the weak interactions. So when people began to observe the decays of the neutral K meson, the neutral K meson, it turns out, has two decays. It has a decay to pi plus pi minus, and it has a decay to pi plus pi minus pi 0. And at first it was thought that the particles that decayed to these two final states were two different particles. Because after all, the neutral K meson belongs in the same multiplet as the neutral pi meson, actually all the pi mesons. It is well established to have intrinsic parity -1. The pion also has intrinsic parity -1. So this situation here has intrinsic parity +1. Maybe you could say -1 to the L, but this is also a spin 0 state, so L must be 0. Here we have intrinsic parity -1, and this works out right. These guys have intrinsic parity -1 times -1 to the L, but then you can, you guys did the first problem set. You can look at the Dalitz plot and realize that L is equal to 0 when you study the Dalitz plot. So there's some kind of contradiction here. A particle with odd parity can either, if parity is conserved, a particle with odd parity can either decay to a particle with, to a final state with, if parity is conserved, a given particle has a parity assignment. So it can either decay to odd parity or even parity, but not both. If the same particle decays to final states with both even and odd parity, that means that parity must be violated. And so parity was known to be an extremely good symmetry of atomic physics, nuclear physics. It was really the insight of T.D. Lee and C.N. Yang to basically go back through the literature and try and figure out what were the circumstances under which parity conservation had been tested. And what they realized is that if beta decay could be ascribed to a completely new interaction, different from the strong interactions and the electromagnetic interactions, that actually the parity conservation in that interaction had never been tested. And apparently, from this observation here, it failed. And so this was the crucial clue. Yes?
How do you see L from the Dalitz plot?
I'm sorry?
How do you see L from the Dalitz plot?
Basically, if the points are uniform over the Dalitz plot, that means the matrix element is constant. And that's a very good approximation for this process. If the matrix element is constant, there's no orbital angular momentum. In order to have orbital angular momentum, you have to have nodes. that are visible as lines of zeros on the dot. Okay, so Li and Yang proposed that there was a new kind of interaction called the weak interaction, which was totally separate from the then mysterious strong interaction, and that the weak interaction violates parity. Well, that just opened the floodgates to new explanations. And very rapidly after this proposal, a lot of people in the community thought, well, if the weak interaction violates parity, maybe the weak interaction violates parity maximally. And of course, people had been playing with relativistic field equations and were fond of the Weyl equation, which is much simpler than the Dirac equation. So in a very short time after this discovery, Feynman and Gell-Mann and independently Marshak and Sudarshan wrote down the following theory that they proposed described the weak interactions. They said you're supposed to add to the theory of the strong interactions a Lagrangian with some coupling constant, which we'll get to in a moment, J mu plus, J mu minus, where J mu plus is a current which has an indefinite parity. Where J mu 1 and J mu 2 are the isospin currents that I wrote down yesterday. So this is the isospin raising operator. That would give it a positive charge. Remember, isospin raising turns a pi 0 into a pi plus. And then what they wanted to write was so-called V minus A, a vector current minus an axial current. This is even parity. This is odd parity. And so something interacting through this current would have indefinite parity. Maybe it's not so easy to understand what's going on in that equation, so I'd like to write that equation in modern language. And I'm ignoring something called flavor mixing, which we're going to discuss next Wednesday. In modern language, that equation would be U bar gamma mu d left, and that's it. Maybe we should add something for the leptons, which I've not included there. Nu bar e, gamma mu e. Only the left-handed parts of those fields participate. And I probably need a factor of 2 or something in order to get that normalized in conjunction with this equation. Oh. No, I think this is probably right. Okay. The factor of the square root of 2 comes because this constant had been defined previously by Fermi in that Fermi theory of the 1930s that I told you about. When you add this extra term, you have to add a factor of the square root of 2 so that the formula for beta decay has the same normalization. This G sub f is called the Fermi constant. Its value is about 1.17 times 10 to the minus 5 over GeV squared. It has the units of energy to the minus 2. Okay. This was a very bold proposal at the time. The phenomenology of beta decay, so Fermi allowed operators of any symmetry to appear in this effective interaction. He had V, he had V times V, he always had parity conservation. V times V, A times A. Also, S times S, scalar times scalar, and tensor times tensor. And at the time that Feynman, Gell-Mann, Marshak, and Sudarshan wrote their paper, the experiments actually favored scalar and tensor exchange. And if you read the Feynman and Gell-Mann paper, it's a really fun paper to read. They say at one point that the experiments disfavor this hypothesis, but the hypothesis is so beautiful the experiments must be wrong. And indeed, they did turn out to be wrong. Shortly after their paper appeared, Feynman and Gell-Mann received a letter from Valentine Telegdi, a very famous experimenter at the University of Chicago, which said basically he had applied the Feynman-Gell-Mann theory to some very detailed measurements of beta decay and found discrepancies of the order of 20%. And therefore, he said, the FG theory of beta decay is no FG. So the story is told. You can't always trust everything in this book. But the story is told in You Must Be Joking, Mr. Feynman. Feynman there claims that he counseled Gell-Mann, well, let's just wait and see what happens. And apparently 2 days later, they got another letter from Telegdi saying that he had neglected the nuclear recoil correction. And when he put that in, everything was perfect. So this is a very interesting theory, and I'm now going to try and work out some predictions of this theory to convince you that it really does a beautiful job of explaining many aspects of the weak interactions. Yes?
V means vector and A means...
V means vector and A means axial vector.
Is that like a pseudo-vector?
Yes, a pseudo-vector. It's a vector that is spin 1, but it has the opposite parity that you would expect for a vector. So odd in the time component and even in the space component. Okay. So let's now discuss some predictions of the V minus A theory. First of all, it predicts that if you have an electron which is emitted in beta decay, that electron should be left-handed. Ta-da. Well, this actually can be measured. You have a beta decaying substance, electrons come out, you analyze their polarization with Muller scattering. Of course, electrons, beta decay doesn't involve completely relativistic electrons. The difference between the neutron and the proton mass, you remember, is just a little more than an MeV, which is roughly double the electron mass. In a nucleus, the energies of the nuclear neutron and proton levels are shifted around. In fact, in a nucleus, it can even be the other way. The protons can be in higher energy states than the neutrons, so that you can have beta plus decay. And so over an array of nuclei, you have different velocities for the emitted electron, and those velocities are comparable to, but not exactly, the speed of light. So the regularity that's predicted is that the left-handed, the polarization of the electron should be, maybe I should say the helicity of the electron, should be minus a half, that is left-handed, times the velocity over c with which the electron is emitted. And on page 2 of the slides for this lecture, I have a graph of the data. And what you see is that, with some scatter due to the uncertainty in polarizing nuclei and measuring electron polarizations, it actually works extremely well. This is a very beautiful regularity in the physics of electron emission in beta decay. However, to get a really precise test of V minus A, one would like to go to a system where no strong interactions are involved. And there, the nicest place to go is the muon decay. I don't know, how many of you read the book called The God Particle by Leon Lederman? Yeah, there's much not to recommend about this book, especially the title. But the chapter on this subject is actually very interesting. After the suggestion that weak interactions violated parity, some experimental proof of this was sought. and C.S. Wu at Columbia University got together with people at the National Bureau of Standards. You're in the wrong lecture. Okay. It's today. Or it's weak interactions. Got together with people at the National Bureau of Standards to do experiments where you had a polarized nucleus. And the idea of those experiments was if this nucleus is polarized this way, and it emitted beta decay electrons preferentially upward, the parity conjugate of this would be the following. The nucleus would be spinning the same way, because spin is even under parity, but the electrons would be emitted in the opposite direction. So if you observed a preferential motion of the electrons upward, then that would be proof of parity violation. And in fact, this experiment did give the first experimental proof that the weak, if you like, direct proof that the weak interactions violated, that beta decay violated parity. However, during the course of this experiment, a group of people at Columbia University were talking about this experiment and other methods for verifying parity violation in beta decay. And they realized that up the river, they had a cyclotron which could produce muons. And in muon decay, parity violation should be 100% effect. So all you had to do was go in there, run the cyclotron over the weekend, and observe 100% asymmetry from parity violation. And indeed, they did it. And their paper was submitted almost simultaneously with the paper of C.S. Wu. This is, oh my God, I should have written down the names. This is Letterman, Steinberger, both of whom will appear later in our story. I've forgotten the name of the third author of that paper. Please excuse me. Well, about 2 days later, but not in time for that particular issue of Phys-Rev Letters, an article was submitted by the same fellow, Telegdi, who had measured muon decay from cosmic rays and come to exactly the same answer. And so with those three experiments, the parity violation of the weak interactions was established. OK, well, now let's analyze how this muon decay stuff works. The effective Lagrangian for muon decay, the thing from which we're going to get a Feynman rule, is now the following. I think the matrix element really should be 4i, that factor of 2 comes squared, g sub f over 2. So we're going to have a muon coming in. We're going to have a muon neutrino going out. Through this interaction, an electron will go out and an electron antineutrino. And so we get u sub left of the nu mu, gamma mu, u, again, the left-handed projection of the muon, u bar left for the outgoing electron, and v for the outgoing electron neutrino. And so basically what we need to do is to take the matrix elements of this expression. Let me imagine that the muon is at rest and that it's spin polarized along the 3-axis. And then the big spinner for the muon is going to look like this. And I'm only going to take the left-handed part of it in conjunction with this formula. Similarly, we can write the other spinners. I think what I wrote down here is to put the electron neutrino at an angle of theta with respect to the muon spin. And it's an antiparticle. It has a V spinner, twice the energy of the electron neutrino. And what would be here is minus sine theta over 2. cosine theta over 2. Okay. And the other spinors we'll deal with in due course. Now, if these are left-handed particles, what really should be here is the matrix sigma bar. And sigma bars obey a very convenient identity called the Firth identity. If you like, beta and delta are left-handed indices, and alpha and gamma are the conjugates, which are right-handed indices. And so this must be proportional to a scalar in the left-handed indices, a scalar in the right-handed indices, and an appropriate constant, which turns out to be 2. And that makes evaluating this expression a lot easier. It becomes 8I over the square root of 2, G sub f, UL dagger alpha, epsilon alpha gamma, yeah, this is the muon neutrino. Epsilon alpha gamma with the electron. UL of the muon, epsilon beta delta with the V of the electron antineutrino. And so actually, that's why I wrote out this spinor, because this product here is now very simply evaluated. It's the square root of 2 times the energy of the neutrino times the mass of the muon times it would be the sine of theta over 2. Uh-oh. What did I do here? Oh, I'm sorry. Right, I put the muon spin in the plus orientation. Please excuse me. Then this would be the cosine. Okay. So now all that's necessary is to evaluate this thing and integrate over phase space. Probably the nice trick here is to notice that this object, well, this object here is Lorentz invariant all by itself. So we might as well just choose another orientation of axes where the electron and the muon neutrino are going back to back. Then the muon neutrino would have an energy of 2e neutrino. Both of these are left-handed particles. So let me write the U for the electron. That has to be left-handed. The U for the neutrino is 2e times the neutrino. That has to be left-handed, but it's going backwards. So we rotate the spinor by 180 degrees, and we get that. And then evaluating this expression, you can see that this is 4e electron, e neutrino to the 1/2 in that frame. And this is exactly the square root of 2pe dot p nu, which is now appropriate to be evaluated in any frame. So now I think we're all set. We can write the whole square of the matrix element as two e nu times the mass of the muon times cosine squared theta over 2, which is 1 plus cosine theta, the 1/2. So this is the angle that I wrote over there between the muon and the antineutrino. And then this is Pe minus P nu or PE plus P nu squared. And I can equally well write that as P mu minus P of the antineutrino squared. And so actually everything is given in terms of the angle of the, in terms of the properties of the antineutrino. This quantity here would just evaluate to m mu squared times 1 minus the, minus 2e mu e, please excuse me, m mu squared times minus p mu times p nu. And now if I go to my three-body phase-space variables, so this is x of the electron is 2 p mu minus p electron over the mass of the muon squared, and x of the antineutrino is 2 p antineutrino dot p mu over mass of the muon squared. This quantity here becomes m mu squared times 1 minus x of the antineutrino. And so now if I'm evaluating this matrix element, I get this expression times, from up here, m mu squared times 1 minus x of the antineutrino. And this quantity here is also x of the antineutrino. And now you plug this into your formula for three-body phase space, and we come out with the following expression for the decay rate. 1 over 2 m mu, the integral over three-body phase space, 128 pi cubed, the integral over x of the electron and x of the antineutrino. Let's write it that way. And then this expression here, so it has basically the structure x nu times 1 minus x nu bar. So 1 minus x nu bar from here and x nu bar from there. And then all that's necessary is to get the coefficient right, which is, I guess, the 64g Fermi squared. Sorry, I've really messed up with my notation what the coefficient is, but it's the square of what's in front of that. There's several factors of the mass of the muon. This is probably all messed up. Let me write the correct formula. I'll write the correct formula in just a moment. Yes?
The calculation of the right side, is that because it has a metric square to 1/2 and anything is equal to metric
Oh,
square?
it's always to the 1/2. But then when I square the matrix element, I'm going to get this to the 1. And similarly here, there's a square root of E nu. But when I square the matrix element, it becomes a whole factor. Okay. Good. So now what we can do is the phase space integral. Now, you guys have studied this phase space. You know how it works. We can write this in terms of xe and x nu bar. What we want to do is to integrate this expression, x nu bar, for fixed xe from here to here. So this goes from 1 to 1 minus xe, the integral dxe from 0 to 1 of x nu 1 minus x nu bar. And if I now do that integral, this thing here will become xe squared over 2 minus xe cubed over 3. And this will be integrated dxe from 0 to 1. And then finally, if you get all the factors right, you'll come to the following final result, that gamma is equal to the Fermi constant squared the mass of the muon to the fifth, that's just required by dimensional analysis, and 192 pi cubed. Okay. Now, from this equation and the measured muon lifetime, we can now get the factor of the Fermi constant extremely accurately. And actually, the current value is 1.16637 plus or minus 0.00001 times 10 to the minus 5 over GeV squared. So this number, by the way, includes QED corrections. At that level of accuracy, you have to worry about things like the muon coming in and radiating a photon before it beta decays and things like that. But with proper analysis and correction, the fundamental Fermi constant is given with fantastic accuracy by this measurement. We've also found out, of course, the neutrinos are not observable. They escape from the detector. But the electron is very visible. And so we can see exactly where that's going. And it's given by this formula. D gamma dE of the electron is proportional to the electron energy squared times 1 minus xe over 2/3, like that. So if you look at what this expression looks like, it's an expression which is very shallow. The maximum value of xe is 1. It's very shallow at low values. It comes up and it has a maximum at the peak. And so if you just plot this function, you'll see it looks exactly like that. And if you measure that function, you'll see what the measurement is on page 3 of the slides. And you'll see that the measurement actually looks unbelievably like that function. So it really works, this theory. It tells you in great detail what the electron spectrum should look like in mu decay. Now, there's one more detail. Yes?
How do you know what things can go into and come out of such a weak interaction vertex?
Sorry?
How do you, maybe this should be obvious at this point, I don't know, but how do you know what kind of particles can interact with such a vertex? Because it's not just these four, right? There can be different things at the legs of that vertex.
Oh, but this is muon decay. So you can ask, so I wrote down a Lagrangian. I wrote down the weak interaction. Okay, so there's this current. I didn't tell you what else is in the current. But in principle, any kind of quark or lepton could be in the current. But the muon only weighs 105 MeV. So it can only decay to things that are lighter. And there aren't many standard model particles lighter than the muon. In principle, there could be quarks, but we know that the lightest state made of quarks is the pion, which is heavier than the muon. So the muon can't decay to pions or any other strongly interacting particle. The only thing available is the electron and neutrinos. And so you look for those terms. There's this term, and there's a corresponding term for the muon. And that's it. Those are the only things that can participate. And so I just put those two terms together, and I got this interaction. Okay. Now, if you had a heavy lepton, then that thing could also decay to quarks. And so the lepton tau, if I just have exactly the same theory, that could decay to an electron and neutrinos in the way that is described by this equation. It could also decay to a muon and neutrinos. One of these would have to be a muon neutrino. And it could also decay to quarks. So, for example, a tau could decay to U bar D and a tau neutrino. And this would materialize as a pion, a kaon, or something like that. For the tau, all of these modes are observed. And the ratio of those branching ratios, actually, the individual absolute branching ratios, because we also know the lifetime, are in good accord with this theory. And absolutely, yeah. And in fact, there's a prescription. You write down the full current, which I'll do next week, and you square it. And anytime you see terms that have the relevant, the thing that disappears, anything can appear and it has to be energetically allowed, then that can be there. I might just give you tau decay on the problem set next week. Good. Okay, now there's one more aspect of this decay which is also very interesting. One of the things that I argued to you in the process of doing this computation is that the distribution between the muon and the electron antineutrino was a 1 plus cosine theta distribution. So let's think a little about how this works for an electron at its maximum energy. If I have the electron at the maximum energy, it's left-handed. At the maximum energy means the other two particles are going in the opposite direction. So the electron antineutrino and the muon neutrino have to be going in the opposite direction, and they have to be collinear to get the electron up to the maximum energy. Now, if this guy has an angular distribution 1 plus cosine theta, that means at the maximum energy, this guy has an angular distribution 1 minus cosine theta. And that's extremely interesting, although I think you can see the result just from angular momentum. If the spin of the muon is pointed in that direction, and the electrons are left-handed, you never expect an electron to be at its maximum energy coming out in the direction of the muon spin. So you can do that experiment. And it was done, actually, here in Canada at the Triumph accelerator in Vancouver. You take muons, you produce muons from pion decay, you let the muons come to rest, and you let them come to rest in a magnetic field, and then you process the spins in the magnetic field. And whenever the spin comes around, and then over here somewhere you have something which is a detector of electrons. In fact, what you have is a big bending magnet, so you only choose the electrons exactly at the maximum energy. And then over here you have a detector of electrons. So what you notice is that every time the muon spin comes and points to the spectrometer here, you get 0. And I think I put the data on the next slide. So there's a map of the experiment on the next slide, and then the data on the following slide. And you see it really works. You get essentially extinction down to a few percent, which you can explain in terms of the depolarization of the muon when it stops and the intrinsic uncertainties in the experiment. So somehow this V minus A theory is incredibly successful at explaining all the details of muon decay, including the polarization. Okay, so now I want to show you one more very persuasive test of V minus A, which is in pion decay. So you remember I told you in the first lecture that the pion, in principle, can decay both to an electron and a neutrino, and to a muon and a neutrino. And normally you would expect that there's more phase space to decay to an electron, so this decay would be a little larger. But in fact, it's smaller by a factor of 10 to the 4th. So can we understand that? And the answer is that the V minus A theory actually gives a way of understanding that. So what I'd like to do is to just gather up a bunch of things that we've said in the course up till now and compute this decay rate. So here's the matrix element. It comes from the basic current 4GF over the square root of 2 times, we want to, let's say, produce a muon here. So there's a mu bar left, gamma mu, neutrino, muon neutrino left-handed. And then we want to annihilate a pi plus So we want something like u d bar, also left-handed gamma mu. So that's the interaction vertex. OK, so now how do I evaluate the strong interaction part of this? Well, I just noticed that this guy here is equal to 1/2 and a minus sign 0 d bar gamma mu gamma 5 u. Okay, this is V minus A, so I'll take the gamma 5 part of the current. And because I have a projector instead of just the left-handed projector is 1 minus gamma 5 over 2, so I need to take into account that factor of 1/2 there. Okay, now this thing we discussed in the previous lecture, and I told you that that's equal to f pi times the momentum of the kaon, and because we have charge states, there's an extra square root of 2 that appears there. So now we can just take this result and plug it in here, use Feynman diagrams for this part, and you can work out the answer. So what we have now is 4gf over the square root of 2. There's a 1 over the square root of 2 from here. There's an f pi. There's a k mu. Now we have from this something like u bar left gamma mu v for the muon system. Now, let's dot this into there. So we'll get u bar left k slash v. Let me draw the diagram. In comes the pion like this. The muon comes out with momentum p, and the neutrino will come out with momentum q, let's say. So k is equal to p plus q. And now what I'd like you to notice is that p slash on u is the mass of the muon, and q slash on v is 0. So this expression is proportional to the mass of the muon. If it were an electron, it would be proportional to the mass of the electron. And so when you work out all the details, it's actually in the notes, and I won't go through it. You come to the following formula, that the pion decay to a mu plus and a neutrino is equal to g squared, f pi squared must appear, the pion mass cubed, because that's the thing that has the correct dimensions. There's a 4 pi. There's the mass of the muon squared, which comes from here. And then phase space gives you another factor of 1 minus m mu squared over m pi squared squared. Sorry, half of that comes from phase space, and half of that comes from evaluating this matrix element. OK, for the electron, we would have the electron mass here. And so what you would naturally have is gamma to go to the electron over gamma to go to the muon would be something like me over m mu squared times the ratio of these phase space factors. If you actually put in the numbers here, it's 1.28 times 10 to the minus 4. And the experimental value is 1.23 times 10 to the minus 4. So it really does a very good job. The physical explanation for this suppression is the following. Again, it has to do with the chirality of the weak interactions. The pion is a spin 0. The pion is now decaying to a muon neutrino and a mu plus, let's say. The muon neutrino is always left-handed. The mu plus must be also left-handed. But now let's try and get this straight. The mu minus is always left-handed. The antiparticle of a mu minus is a mu plus, which is right-handed. So if you make the mu plus left-handed, this is helicity violating. And therefore, it has a suppression factor of the mass of the muon divided by the energy of the muon. For the muon, this is not a big deal, but for electrons, this would be a very big deal. And it accounts for this large suppression of the electron mode. Oh, by the way, as a byproduct of this calculation, we get the value of f pi. So if you plug in the numbers for the pion decay rate and the Fermi constant, which we've already determined, you find that f pi is 92 MeV, as I claimed yesterday. Okay. Now, there's one more topic that I wanted to discuss with you, which also gives some very beautiful tests of this weak interaction theory, not only for electrons and muons, but also for quarks. And that's the subject of deep inelastic neutrino scattering. Now, I asked you to write some formulae for this based on an effective Lagrangian. Now we have the effective Lagrangian. So let me write down the answers that you should have or will achieve in your problem set. So you remember that for deep inelastic, let's just do this over here. For deep inelastic electron scattering, we found a formula of the following type. d sigma dx dy is equal to some constant that appeared here, a 1 over q squared squared, and then a structure which was 1 plus 1 minus y squared. And this structure here came from the helicities. For example, a left-handed electron scattering a left-handed quark gave this term, and a left-handed electron scattering a right-handed quark gave this term. Now, in the weak interactions, everything is left-handed. So if I look at, and then these terms were related, by the way, to some parton distributions for the various flavors of quark and antiquark. Now, if I have neutrino proton scattering turning into a muon plus anything on the hadronic side. So the neutrino comes in, it turns into a muon, it mediates with this current-current interaction. Some parton comes in, another parton goes out, and the fragments of the proton go off like that. That's the diagram we're computing. I claim that this is the result you should find. First of all, there's no 1 over q squared. That's associated with the photon. Instead, there's a g Fermi times s over pi. Then we get x, f. Well, let's be a little careful here. The basic reaction would be the neutrino going to a muon. And if you just think about charge conservation, that would turn a down quark into an up quark. So only the down distribution appears here. This guy is left-handed, and this guy is left-handed. So we get that. The other possibility that we have is to turn an up bar antiquark into a down bar quark. In that case, this guy is right-handed. And so we'll get this. And I think in the problem set, I asked you guys to verify this by explicit computation. So that's the formula. For antineutrinos, it's exactly the opposite. The up quarks go here, and because of the mismatch. This guy is right-handed. This guy, the u, is left-handed. You get a 1 minus y squared. And then you get 1 for the d bars. So this is really pretty cool. If there are mostly quarks in the proton and not too many antiquarks, the neutrino scattering should have a flat distribution in y, and the antineutrino scattering should have a 1 minus y squared distribution. And if you look back at the slides that I gave you on the determination of parton distributions, you can see that it works extremely well. I think I put one of those, if you don't look back, if you just look at today's slides. There's a measurement from the CDHS experiment, which was a big neutrino experiment done at CERN in the early 80s. And you can see the y distribution for neutrinos with the white points and for antineutrinos with the black points. And it is a very striking effect. And that effect is a direct reflection of the helicity of these neutrinos and the chirality of the weak interactions. Okay, now, there's one more thing that I guess you need to know about, well, I guess I could spend a lot of time telling you how you get neutrinos to do this experiment in the first place. But if you're curious, you can ask me about that offline. Instead, I'd like to tell you about one other thing that these deep inelastic neutrino experiments discovered, beginning with an experiment at CERN in the early 70s at a big bubble chamber called Gargamel. So those of you who have your French culture in hand will know exactly what Gargamel or who Gargamel is. But at CERN in the early 70s, it was the largest bubble chamber in the world. And they shot neutrinos into it. And in addition to observing these reactions, they also observed reactions where apparently the neutrino would stay a neutrino, but a proton going in would get disrupted. And on the next slide, I have a picture of such an event, an actual event picture from the CCFR experiment, which was an experiment at Fermi Lab done in the 80s. So the first picture is a picture of a charge current event. A neutrino comes in, a muon goes out, a nucleus is disrupted. The detector is layers of iron insulator. And you can see there a picture of the nuclear disruption in the bottom. These are the x and y plane views. And then one track, which is very penetrating, that goes out and goes a very long distance. That's the muon. OK, now turn the page. You see a picture of an essentially completely identical event, but that track is missing. And you can convince yourself that it wasn't just that the muon escaped. The muon, it's a huge iron detector. It could really contain the muon and measure its track. It's that the track is not there. And in fact, what's going on is this transition. So to understand this transition, what you have to do is to generalize the V minus A theory. And what I'd like to do is write down the appropriate generalization. And for the moment, let me just tell you that this generalization is very well tested in these deep inelastic neutrino experiments. We'll discuss its origin next week. What you need is delta L is equal to minus 4 G sub F over the square root of 2. And then we have J mu. So I can write J mu plus J mu plus is 1 plus I2, right? So J mu plus J mu minus I can write as J mu 1 squared plus J mu 2 squared. And then what you're supposed to do is you're supposed to add J mu 3 squared. But it turns out that's not quite the right thing to do. What you're supposed to do is add the following quantity. So what you have there is J mu 3 minus SW squared J mu EM, which is equal to F bar F bar gamma mu, a left-handed projector, the third component of isospin, minus a parameter called SW squared, which I will explain next week, and the electric charge associated with that flavor, and F. So this is maybe an odd thing to write. This part is left-handed, but this isn't. This is the electric charge current. And then you end up with some interesting quantum numbers. For example, for the left-handed up quark, it has isospin a half. It has a charge of 2/3. For the right-handed up quark, this is absent, but the second term is there. And so those are the charges of the various helicity flavors of quarks under this current. The explanation for the full structure here I'll give next week. But there's a part which is easy to understand, which is that if you neglect this, then it's completely symmetric under an SU2 symmetry, where you have 1, 2, and 3 each squared. Now, this then gives rise to, if you just plug that through very carefully, it gives rise to formulae for neutrino so-called neutral current deep inelastic scattering. These are called neutral current reactions. And I've written the formulae in the notes. I think I won't write them on the blackboard. There's a very interesting test, though, of these relations. And that is that you can write a formula that removes a lot of unknowns from your measurement in the following way. Let me write little r is equal to the ratio of cross-sections for anti-neutrino charged current reactions and neutrino charged current reactions. Then it turns out that you can manipulate, and this is equal to, and let me assume that I have an isoscalar target. That is something like iron, which has roughly equal numbers of protons and neutrons in it. So then I have the same up quark distribution as down quark distribution in the target. Yes?
One thing. When you write the current J plus U,
yes?
you said J1 plus J2. The 1 and the 2 are indexes of 4 hours.
Isospin. Isospin. So this here would be, let me write Q gamma mu sigma 1 over 2 Q, where Q now is UD. So that is J1. And then J2 would be the same thing with the sigma 2 here. And sigma 3 is this. Okay.
How do we know that electron in the first place?
Sorry?
How can we know if electronic number is constant or not?
How do I know there's a neutrino in the final state?
No, not that. How do I know that if I produce an electron, I have to produce an antineutrino? If I produce a muon, I have to produce an antineutrino.
Okay. Well, for muon decay, I think the answer is that this formula that I derived for you, and I showed you that it works extremely beautifully, it just wouldn't work if I didn't have 3 particles in the final state.
But if I say that I produced an electron,
Yes.
and a neutrino, not any other neutrino,
Yes.
would I get the same answer?
Oh, no, you can work it out. You get a different distribution for the energy of the electron. So everything that curve that I drew for you depends in detail on the Lorentz structure of the interaction. So there's a fellow named Michel who wrote down the most general Lorentz structure. And then over many years, people measured muon decay to constrain the so-called Michel parameters. And the answer is that to within % accuracy, that Lagrangian that I wrote for you is exactly right. So now, so now this is equal to, remember, yeah, no, that's right. So this guy has the quarks with 1 minus y squared distributions and the anti-quarks with 1. This guy has the quarks with 1 and the anti-quarks with 1 minus y squared distributions. And then you could also imagine that you could average this quantity over some region of your detector acceptance, so it's very convenient. In terms of this quantity, you can work out that the ratio of neutrino neutral current to neutrino charge current reactions is given by the following very simple formula. 1 minus SW squared plus R, which you in principle could measure experimentally, times, please excuse me, 5/9 SW to the 4th. And then the R comes in only here, and you can measure it experimentally. And similarly, R nu bar, which is the same quantity for anti-neutrino neutral current experiments, is given by the same formula with a 1 over R here. Good. So the value of R is maybe 1/3 or something like that. And so then what you can do is to plot these quantities against one another as a function of SW squared. When you do that, you get an interesting figure, which I've shown on the last slide here, which is a curve in the R nu versus R nu bar plane parametrized by the value of the unknown parameter SW. And what you can see is the following two things. The curve has a funny shape. In the 70s, when this was discussed, it was called Weinberg's nose, for reasons that might be obvious. The data, in principle, could be anywhere on this plane, but in fact, the data lie on the line, which is swept out by these equations. And where the data is tells you what the value of SW is. So the value of SW that's picked out is very close to 0.23. And so using those facts, we will, in the next lecture, construct a fundamental theory that leads to the effective theory that I described to you today. And of course, Mr. Weinberg will be the champion of that, and we'll see how it all works. So that's enough for today. We'll take the next step tomorrow. Yes, or Monday. Those are the most accurate. Actually, on Tuesday, we're going to determine SW to 4 significant figures. But that doesn't involve this kind of experiment. Okay, thank you.